Welcome to the Egg Drop Lab, a small-scale version of the Big Primer project in December, where we measure impact time in the laboratory. We are here to answer the question, how big is a safe impact time and how small is an unsafe impact time? Are we measuring in nanoseconds, microseconds, milliseconds, whole seconds? And once we've figured out what constitutes a safe impact time, what kind of designs give us that safe impact time? If it worked on the small scale, on the force plate from a drop of 2 meters, can we scale it up to drop the eggs over the balcony with the whole school cheering for the Big Egg Drop project? Since we only have one period design, I bring you the following advice, courtesy of physics classes past. Number 1, a box does one thing, and that keeps the egg from falling out of your egg drop container. Do not start with a box. One sheet of paper provides practically no impact time whatsoever. It is completely negligible. Make sure that your egg is securely in a place where it will not fall out of your container. If you want to make a box, fine, make a box, but don't start with a box. And notice that a box takes a lot of paper, and you could strap your egg in with seatbelt straps taped into 3 or 5 places with much less paper. Next thing everyone generally starts with is crumpled paper. Who here sleeps on a mattress filled with crumpled paper? No, not even in third world countries? No, nor a pillow? Nope. Crumpled paper provides negligible impact time. It might protect your egg from a drop of 2 inches. For 2 meters, it is not going to fly. If your egg drop container is based on it will be crumpled so it will be soft, it is simply not going to work. Oh, but wait, this is not crumpled paper. This is artistically folded paper. Oh dear, that impact time was also negligible. If your design is based on the softness of crumpled paper, it might work from 1 inch, but from 2 meters, forget it. You're going to continuously ask the question, it's good, but is it good enough? Having a measurable impact time is about good geometry. If it's too flimsy, it'll crush in no time whatsoever. If it's too rigid, it won't crush at all, and you'll be right back where you started with a very, very short impact time. If you studied the shape in freshman geometry, that's probably a good sign. It should take some time to crumple up. Freshman geometry will also tell you that the most stable shape there is a triangle, so plenty of people will do this in 3D and say, aha, now success. Take a look at that design for a minute. What are the chances that that egg is going to land directly on that single point like a ballerina? Basic geometric probability says there are 359 other directions it might fall in, and the 1 out of 360 chance that it lands right on that single point is pretty slim. Look up center of gravity or center of mass in your book, and you will see that it's not just Murphy's Law. It is a foregone conclusion that if you drop an egg with 1 cone protecting it, it will fall over on its side. And what is protecting the egg on its side? Bless my soul, it's that 1 sheet of paper that we knew was bad news. This is a cracked egg. All right, so we take it as a foregone conclusion. If you don't want your egg drop container to tip over and spill your egg out, it will probably do so just to spite you. Look up center of gravity. So let's put the egg in 2 cones, 1 protected on the top, both the top and the bottom, whereupon we have the same problem. It's going to fall on the side where you have 1 sheet of paper protecting the egg. So, conclusion, protect your egg on all sides. It's not just a box with stuff in it. It's a box with huge geometric structures coming around it on all sides. If you've looked up center of mass and center of gravity and you found a good physics way to make your egg drop container fall straight down, you are in great shape. If you haven't wanted to do extra physics homework, assume that protect the box on all sides means it might well give you some nice radial symmetry. You want good, robust geometric shapes that will really be able to take a pounding and dent and damage that D-displacement, and you're going to want to tape them together very well. Most designs that looked absolutely fine in theory and then wipe out in the lab are where you had these 2 wonderful cylinders taped together to make a landing pad. Down they fell, whomp, they completely wiped out, and the one flimsy piece of tape or the three flimsy pieces of tape just didn't cut it. Notice that when your friends take their final projects to the balcony in previous years, you will see some pretty dramatic taping jobs. If something is supposed to stay at a 120-degree angle, you tape it so it stays at a 120-degree angle. Ask yourself, force times displacement equals change in energy. We want less force. How much displacement do you want? How much structural distance do you want between your egg and the ground? How far should the egg be from the landing zone, and what should be in between there? You will have 30 seconds or less to tape your egg into your container and make sure there is something really structurally sound in between the sides of the bad news box and the ground. You will then drop it onto the force plate and measure the force that it feels. Do not miss the force plate. Know that your measured flight time and your calculated flight speed or flight time might be different. Consider, are you expecting free fall conservation of energy, or are you expecting air resistance? Come in with your design ideas ready, and good luck.